Recall that for a separable ordinary differential equation, we can separate the variables by putting the y terms on one side and the x terms on the other side. And that allowed us to integrate both sides of the equation. And therefore on the left hand side, we get some antiderivative of the reciprocal of g of y. So I'm just going to call that h. And that's equal to the antiderivative of f of x plus a constant of integration. And then given that y is a function of x, we solve this equation for y, and then we obtain y of x on the left hand side. So effectively what we get is y of x is equal to some function of x plus c, which is a constant. And this is the general solution because we can have an infinite number of values for the constant c. So therefore what we do is apply an initial condition. So y at x equals a is equal to y naught. And therefore what we got on the left hand side is y of a, which is equal to y naught, and that's equal to u of a plus c. And therefore that allows us to obtain a specific value for the constant of integration. And then we substitute it into here to obtain a particular solution to the function y of x. So essentially there's one particular solution that passes through this point, x equals a and y equals y naught. And we'll get some practice with this method in the coming example problems. Let's find a particular solution to this ordinary differential equation, where we're given an initial condition, and then we're asked to compare y of 0.4 using the exact solution to the approximate solution using Euler's method. So what we're going to do is put this in a form where we can separate the variables. So therefore dy on y is minus dx. And then integrating both sides, we obtain a natural log of y is equal to minus x plus a constant of integration. And therefore y is equal to e to the power of minus x plus c, which is the same thing as e to the minus x by e to the c. And because this is just some constant, then we can write y is equal to some constant by e to the minus x. And now we can apply our initial condition. So when x equals 0, y equals 0.2, that would be c1 e to the 0. So therefore the constant of integration is equal to 0.2. And therefore from this equation, our particular solution is equal to 0.2 by e to the minus x. And now you can substitute for x equals 0.4, and you can obtain y of 0.4 and compare it with the approximate solution we got using Euler's method. And post your answer in the comments. A skydiver's acceleration is described by the following ODE, where g and k are constants, and we have an initial condition of the velocity at time 0 is 0. And find the equation for the velocity as a function of time. So we have the acceleration is equal to g minus kv, and we can separate the variables, so dv over g minus kv is equal to dt, and then integrate both sides. So on the left hand side you can use u substitution, so what you'll get is minus 1 on k by the natural log of g minus kv is equal to t plus the constant of integration. And from here you can manipulate it, so you have the natural log of g minus kv is equal to minus kt plus some other constant. And if you take e to the both sides, we get g minus kv is equal to e to the minus kt plus c1, which is the same thing as e to the minus kt by e to the c1. And this is just some other constant, So we can write g minus kv is equal to c to e to the minus kt. And now you can easily solve for v, apply your initial condition, and write the particular solution, and post your answer in the comments.